Hello. 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 Okay. Hello. Good afternoon. Sorry. Good afternoon, Osmael. Good afternoon, David. Good afternoon, Jamalet. Good afternoon, Sophia. Good afternoon, Amy. Good afternoon, Stephen. He's just literally from 2. He's like not even from a dimension. He's just like from the number 2. That's awesome. Hold on. Okay. Good afternoon, Gianna. And there is a dimension. Yes, Stephen just gained a dimension or 2. Yes. And he just stole a dimension from my board because my board just lost a dimension again. Hold on. Good afternoon, Sarah. Good afternoon, Diana. Good afternoon, Brooke. Good afternoon, Samuel. Good afternoon, Chloe. Good afternoon, Shakia. Hi, Jada. Top of the afternoon, Abdel. Good afternoon, Jasmine. Good afternoon, Jalen. Good afternoon, Brianna. And good afternoon to my board who is coming back, which is coming back. Okay. Okay. All right. We will get rolling now. And good afternoon, Nicholas, who's here. Okay. Okay. I'm just gonna get rolling here. Bottom line, I think we're on the same page that correct me if I'm wrong, correct me in the chat. Wait, hello. Oh, good afternoon, Nicholas. Awesome. Thank you. Good afternoon. Okay, good afternoon, good afternoon. And there goes my board again. This is like, okay, it's like when the cork of life closes a door, my board. No, when the cork of life opens the door, my board closes the window. Okay. Yes, hello everybody, hello everybody. And I actually secretly know that actually Shakia was here before anybody. I totally know that Shakia joined the waiting room, like before I even joined the waiting room. I'm totally aware of that. And then her Wi-Fi signal cut out or something. But just saying for the record, I know Shakia has been, and I'm not being sarcastic. I'm just saying, Shakia, I know you've been here for a long time and that something just happened to your signal. Okay, so thank you and welcome. All right. So my understanding is that this coming Wednesday in 2 days, I will post an exam, your midterm exam. I'll post it sometime prior to 8 o'clock at night. I usually try to post it a little bit early, but the 8 o'clock is the cutoff. Then you're going to turn it in by 12:15 next Monday. Again, all of this is in Google Classroom. I'm just confirming that the exam will be posted Wednesday. You can turn it back Monday, no later than 12:15. Then you show up to class, and that is part of the exam responsibility, is that you show up to the Zoom class on time, having already turned in your exam. The first thing I do that day to start classes, I check what exams are in and what exams are not, blah, blah, blah. And the only exams if any exam comes in after 12:15, that means that the person made a prior arrangement with me that we both shook on and on blah, blah, blah. And that person could have been you, but just didn't need to be you this time. It might be you during the final exam, if you know what I mean. Okay, so it's posted Wednesday night. It comes in right before class on Monday. Then you show up to class Monday. And you do that to show solidarity to your fellow colleagues with whom you hopefully worked very hard on this exam and helped each other and taught each other and explained things to each other that don't make sense when I'm explaining them, but make sense when you're explaining them. Also to confirm, again, between Wednesday and Monday, you can use any resources you want in order to learn the material for your exam, and you can sit down and do it in any kind of untimed fashion you want. But because of all that, I expect that you'll do a rough draft, and I expect that by the time you give me a final copy, it really is a beautiful, proud, well-presented final copy that is not just scratched out at the last minute, blah, 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 blah. I've already given that speech. But if there's I've already gotten texts from people just like clarifying certain things about the rules or what they can use or what, and that's fine. Please do send me texts or emails, just making sure that you get the arrangement. One important clarification that someone did ask, I think this was from another section where their test was already underway, but the only source that you can't use, I mean, you could try, but the only source that you can't use while you're doing the exam is me, which also does not mean you can reach out and ask me clarification questions. Like am I allowed to do this or not? Or certainly you could say, wait, is this an error on page 7 or is it ambiguous? You can reach out to me during the exam, and it's very good if you do, because maybe there is an error that needs to be caught and correct or something. So I won't be offended if you reach out to me, but I won't actually help you with the exam. The main thing that I won't do for anybody, just to clarify this, because it's already come up, what I won't do, you can't try to say like, can you just tell me, Yaverbaum, if I'm on the right track here, like on what I'm doing on part 3. I cannot do that. I'm not going to be offended if you ask, but I hope you're not offended if I say no. There's 1,000 reasons I can't do that. I think you understand all the reasons, but you can ask a friend if you think you're on the right track, blah, blah, blah. Okay. So if there's any issue, any ambiguity, or any concern about your ability to get in on time, like privately deal with me. But other than that, it's posted tomorrow, a Wednesday night, due back Monday. What we're going to talk about today, I can't. And if you have very specific questions about the practice midterm, either today or particularly Wednesday, bring them in. I may or may not get to them or all of them, but certainly if you've been studying and then Wednesday you have questions, if they're concise questions and I can answer them quickly, I'll do that. Today, what I'm going to talk, but other than that, I'm sort of starting to move on. I will be starting to move on to new material. The material I'm going to do today in one moment is a continuation of what I was doing last Wednesday. And hopefully it relates to all this, but most specifically, what I'm talking about today will most specifically help you for question 4, part 4 of the exam, where you really have to use your own words and really create your own answer and full response to explain a whole phenomenon. And I think the bulk of that phenomenon understanding comes from our very last class or any videos associated with that. But today is a continuation of that. If you want to know like what bin in your mind to put what we're about to talk about, it goes in the bin of question 4 on the practice exam. So we're going to start in a second. But can I just get a show of electronic hands that we're on the same page? Like, is everything I just said sound like old news or clear news to you about the exam? Okay, great. Thank you, Gianna. One person. Okay. Thank you, Jamalette. Okay. Thank you, Nicholas. Okay. Awesome. Thank you, Chloe. Thank you, Diana. Thank you, Sophia. Thank you, Jamalette. I said Jamalette. Thank you, Jay Lynn. Thank you, Jasmine. Thank you, Nicholas. Thank you, Osmail. Thank you, Stephen. Thank you, Brooke. Thank you. Okay. All right. So, is that a question? Okay, cool. And that's Amy. Thank you, Amy. Unless that's a question, but I think the Amy IceQ can. Okay. IceQ is having a resurgence in the next format of TCG. IceQ is a big, heavy hitter Pokemon. All right. Okay. So I'm going to change the view. So we're going to go. Yeah. Okay. So this page that you see before you is in part a review summary of where we last left off. And again, I really encourage you to look at the last video, the last class we did last Wednesday, and maybe even the one before it as well. They are all about part 4 of the exam. And that's a place, like that's like the essay part of this test, if you want to think of it that way. Like that's like the free response part where I'm really expecting that you've retained a set of concepts and you've processed them through. And then now you're really showing me, it's really your opportunity to really go free form and really show me that you get something. And of all the places where I would really talk to one another and to really do rough drafts and stuff, it would be part 4. Like that's the most open-ended in a way. Okay. So it starts with the last 2 classes, but the summary, the conclusion that we came to after the last two classes is this equation up here at the top. Right, this equation up here at the top. That equation, which is a function of two independent variables, first time we've ever seen that in physics or science or math, I believe, in your career thus far. It's one output being determined by two independent inputs, right? You know, this one output, vertical position, is being determined by horizontal position and time, right? This function is a description. Now I'm going to speak English now. I would highly suggest you write this down or whatever. Like, the point is that this equation up at the top is, on the one hand, the equation that describes a vast collection of identical vertical oscillators spaced equally along a horizontal axis and staggered in phase by a constant step. I will say that one more time. I feel like it's in your notes from last time. I feel like it's something you really want to get used to. It's also lab 3 and lab 4, but I will say that one more time. That equation, the way we derived it is, and this is the point of question 4, is to really be able to show me how that equation is a correct way to, in one statement, describe a vast collection, a huge collection of identical vertical oscillators distributed equally along a horizontal axis, yet staggered in phase by a constant step. That's what that is, right? Now I'm going to break it down further again and explain each of the terms of the equation. I mean, I feel like I've already done that, but I'm going to try to do it in a different way today. But I want you to know as a whole, that's what that statement is describing. It's a collection of phase-staggered oscillators, right? And in English, what I mean by that is a bunch of oscillators. When I say they're identical, I mean they're all the same. If you're picturing them as masses on springs, then when I say they're identical, I mean they all have the same K, they all have the same M, therefore they all have the same omega, right? And also, let's believe when I say identical, let's assume they all have the same amplitude, the same A, right? So you have a bunch of masses on springs going up and down, up and down, up and down, all in the same way, all at the same rate in time, right? And they're all spread out equally in a horizontal axis, equal, like 0 centimeter, 1 centimeter, 2 centimeter, 3 centimeter, et cetera, right? But the one catch is that they're all staggered in phase by a constant step, such as, for example, the constant step could be, say, pi over 2 radians, right? So what that would mean in English, pi over 2 radians is like a quarter of a cycle, right? So in that example, it would mean like that when they're all the same and they're all doing the same thing, up, down, at the same rate in time, up, down, but they're staggered in phase, so that when the first one stays at its lowest possible position, the next one, right? So when the 0th one, the one at the edge of our horizontal axis, when that one is at the lowest possible position in its vertical oscillation, the next one, say, is at the equilibrium position. And the next one, say, is at the highest possible position. And then the next one is at the equilibrium position. And then the next one is at the lowest possible position, et cetera, et cetera. Now, again, I'm saying that's the rule. That's what we're talking about, the constant step in phase. The example I just gave was when specifically that constant step would be a quarter of a cycle. So one's at an endpoint and one's in the middle, and the next is at the other endpoint, and the next is in the middle. It doesn't have, there's no rule that the thing has to be quarter of a cycle. But the rule is, the idea is that they're all staggered in phase, in the place in their cycle, by a constant amount, a constant step, right? That's what this is describing. Now, again, we're going to break down like what the letters mean and all that again in a second. But that's what that equation describes. Your goal in question 4 of the exam is to walk me through all of that. Like, don't start with that. I'm starting with that right now because we're like 3 days into this, okay? But that's a big part of your conclusion. You're going to draw a big picture, like I did 2 days ago, of a bunch of masses on springs. You're going to show the equation of each one of those individual masses. Like the first one is like y sub 0 is, I mean, like the spring at the edge at x equals 0 would be like y equals a cosine omega t plus k plus like pi over 2 or something times 0, like time plus nothing. In other words, no phase constant for the first one, for the 0th one. And then the first one, the next one would be like y equals a cosine omega t plus 1 times pi over 2 or something like that. And then the next one is blah, 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 plus 2 pi over 2. Now, again, if you really want to, I'm telling you right now as a hint for how to do this exam, like I already given you the basic picture. You look in your prior notes of, but if you want to show me that you get what's going on, in my picture, every time I do this example, I use pi over 2 as an example because I think it's clearer than many other examples because it works for me. But if you really want to show me that you get what's going on, what you might do is consider modeling, like making pictures that are like my pictures, but instead of doing pi over 2 as your example, do pi over 4 or something else that you can imagine, or pi over 3 or pi, right? If you just take my examples and tweak them slightly, you'll show that you get the larger point and you're not just copying me. And okay, and or whatever, things like that. So anyway, what I'm saying is, you're going to draw a big picture. You're going to walk me through, like I did the last few days no problem. Thank you, but no problem. You're going to walk me through to get to that equation at the top, right? You're going to then explain what each of the terms in that equation means, right? Which I'm about to do here again. But your goal is to put together and show how a group of oscillators doing what I just said would be described by that equation. Make sure that by the end of when you're done, each one of the terms in that equation is totally clear. Like, is it a dependent variable or an independent variable? Is it a constant? And if so, what kind? Is it a parameter or is it a configuration constant, et cetera, right? You're going to walk me through the whole thing. Then now, the big punchline of all of this is, and before I go on to the rest of the sheet, I'm saying on the one hand, that is that equation, that function of two independent variables describes a collection of phase-staggered oscillators. But if you stand back and look at a collection of phase-staggered oscillators doing their thing that we just spent all this time describing, you realize that what you've made is a wave pulse or is wave motion. If you have a bunch of objects going up and down, if each one of them is going cosinusoidally in time, so that at any moment you take a snapshot and what you see is a cosine in space. So if you have cosine in space happening cosinusoidally in time, if you have a big ripply curve in space going, or you have, what you therefore have is a ripple propagating horizontally through the whole thing, right? And what you want to tell me this in your question 4 of the exam, which I assure you you're going to do. I mean, it is going to be a question in the exam. Like, your first goal is to set up and show with pictures and words and math how this equation is the proper way mathematically to describe a collection of phase-staggered oscillators. But then your big punchline is, guess what? This equation also similarly then describes a wave pulse or wave motion, because if we do set up a bunch of oscillators this way, what we've created, in fact, is wave motion. And what do I mean? And that's a big leap. We've now, the point of question 4 and the point of this moment in the course is, if you really get what's going on, and it helps to really get the math, but even if you put aside the math for a minute, what we're saying is we've taken a group of particular material, massive, countable, discrete, tangible, thingy thing objects. We've taken a bunch of thingy things and arranged them so carefully. We've arranged their motion into such a delicate pattern of patterns. And I really mean that. I'm not being cute, right? We've literally arranged a bunch of objects so that there is a cosinusoidal spacing of their cosinusoidal timing, right? That's what we've done. And what we've therefore created is a motion that is associated, that we've created a motion for which there is no particular or identifiable or massive or material or tangible or countable or discrete or distinguishable mover. I'm being dramatic because it is dramatic, and I'm saying it a million different ways because your job is to say it your way and show me that you get that once you make a bunch of objects move vertically in their little neighborhoods in a very intricate way, once you take a bunch of objects, a bunch of pieces of wood attached to coils of metal, and you make them each move vertically in this special way, then at the end of the day, what you have is a horizontal motion. And you have a horizontal motion that is observable, measurable, analyzable, predictable, but not material. Let me say it, and I know I'm saying, if you get it, you get it. And then your job is to show me you get it and support it with all the math and all the pictures and everything. But the thing to get here is a thing to get. I'm saying something in the end of the day will move along a horizontal axis. And the thing that moves along the horizontal axis is not a thing. And I'm being literal. I'm not just being cheesy. I mean that we will see a pulse move across the horizontal axis. If we do all of this, right, we will see. And what do I mean by a pulse? I mean like a crest or a trough. And that's where the diagrams down here come into play. I mean, if you watch with your eyes and you video camera, like it's not a misperception, it's a reality that some bump in the metal, a bump, like a raised, elevated, stretchy deformity of the metal will be seen to ripple from left to right. Right? You've done it in the lab. Lab 3 is what we're talking about. You'll see bumps or valleys move at a particular rate through a particular space in a particular time. And the particular space that they move through is horizontal. They will move from one lab partner to the other lab partner, right? I mean, it's specific, it's real, it's concrete, it's scientific, but all that's ever moving, say in the case of lab 3 or in the case of this description, all that's ever doing any motion is metal, and there is no piece of metal that ever makes a horizontal journey. That is the key. You've got to put that somehow in your words when this is all done. You've got to get across to me that this whole math is describing a collection of phase-staggered oscillators, i.e. a bunch of thingy things that are moving in a vertical way, but the result is something that moves in a horizontal way. And the something is a thing, but it's not a thing. I mean, it is an entity, it is a reality, it is observable and scientific, but it's not a material object. There's no piece of metal that goes from one lab partner to the other. I'm going to say one last final way, and then I will move on, I promise. But I swear, I mean, really, this is the point. All the slog that you've slogged through for 2 months in this class to understand differential equations and cosinusoidal oscillations and blah, blah. We're all trying to, in the end, get our mind around. If you felt ever that the math was abstract, it's because what we're trying to get across here is how a bunch of concrete things can come together and make something abstract. And I mean abstract in the literal sense. I don't just mean that it's hard. It might be hard for some of us. It was very hard for me to get my mind around for a long time. But but it might not be hard for you. You might have gotten it 3 days ago. That's fine. But whether it's hard or not, it is abstract in the sense that we are now in a physics class talking about things moving through the material world of space and time. And the thing that we're talking about moving here is not made of material. That's what I mean by abstract. And if you can actually see that, then you're really appreciating something deep, that we have put a bunch of materials together to make a motion that is not material. Wait, I'm just going to pause for a second. And that's what I'm looking for you to explain in question 4. I'm looking for you to walk me through all the individual equations that come together to make this equation that explains how a bunch of material things together can make an immaterial motion. And last thing, your part of your job, you will be done. You will have done it if you have pictures, if you have words, if you walk me through it and you get to this equation up at the top, like that's where you're at. I'm going to move on in a second. I keep saying that, but this equation at the top that you're going to get to is pretty much, then you're going to show, okay, and this, but this is a wave equation, blah, blah, blah. Like it's cosines in time happening while there's cosines in space. But You won't be done unless by the end, you've literally defined each of the terms in this. And I'll tell you right now, in fact, here's a tip for anybody who's still listening to me after this whole rant. Actually, well, yeah, wait, actually, I'll ask you right now, because I'm about to give you a tip from past experience, from grading these exams in the past. I'll tell you exactly where people that thought they knew it still went incomplete and lost points. I will tell you, but let me make sure first. Can you just raise your electronic hand even if I'm being overwhelming or like annoying, can you just raise your hand if you think you get the big punchline? That great. Okay. That's awesome. That was fast, Amy, by the way. Thank you. And Diana and Gianna, and Chloe and Jasmine and Sophia and Jamalette and Nicholas and Diana. Thank you. And Brooke and Brianna and Stephen, Sarah. I never get sick of this. And Osmail. Oh, no. See, also shows that light bulb makes it look like she's raising her hand, but she's okay. So you get, okay. All right. And again, just know this. I'm sure you know this. The fact that I'm yelling about it so much and that I'm so like emotionally excited about it, which I am, I authentically, this blows my mind every semester that I get to talk about this. I swear, it's like the point of why I do it. It blows my mind every semester to get to talk about immaterial motions through the material world. So you'll know, like, question 4 is really your opportunity to really show in your way. Like, you see that I'm taking it seriously. I will take you very seriously if you take yourself if you take your work very seriously on question 4, and just go to town, be as creative. You could be funny if you want, make a cartoon, like express yo apostrophe self on question 4. Here's the tip, since you all just raised your hand. The tip where people like didn't do as well in the past as they could have. They did sometimes a lot of work. They gave pictures that looked like my pictures from the videos, etc. But where they fell short is in defining K. I think it's the first place my eyes actually tend to gaze to when I'm grading, to be totally blunt, okay? One way I can sort of tell if you've really gotten this and where you really now understand Lab 3 and Lab 4 or not. And by the way, I assume that almost nobody understood Lab 3 when they were doing it. That's understood. And if you really think back to Lab 3, you were just at that time maybe getting comfortable with omega, maybe, some of you, but omega was still kind of a weirdo thing. But K was completely this K, which is not the Hooke's Law K, this K was totally brand new to you in Lab 4, came out of nowhere. And if we're honest with ourselves, most of us have no idea what's going on with K in Lab 4. And if we're super honest, we might even be angry about it. Like, we're like, I mean, some people just dismiss it because they're like, I don't even know what that is, like whatever, fuzz. But if you really think about it, K represented for many of us the sort of limit extreme of what was new and confusing or out of nowhere at the time of doing Lab 3. You'll know that you really get this now. If now you really understand what K is, what it's doing there, and if you really understand, for example, the K is what makes this a new equation. This equation was just our old equation until K came into town, right? And specifically KX. It was just a one variable equation that was just dealing with oscillator before now. Everything we were doing was a abbreviated version of this equation that was just space depending on time. That was oscillation. Once you have the KX factor in there, now it becomes oscillation in time and space. Now it becomes a wave. And that's why K is called the angular wave number. So I'm going to start now going down the sheet now, okay? But I'm telling you one litmus test in your mind, if you're hearing me right now. If you really want to make sure that you really nail this question 4, like, you want to make sure that you get all the way to the point of really showing what a impact this K is making on this equation, what difference it's making, what it means, what units it's measured in, where it came from. Like, that's the goal, is to really, you could even make a separate quick hint to, what do you call this, pro tip? Like, you can even make a separate little graph before you get to the end where you have, I mean, if you're listening to me right now, I'll say this quickly, but this is a major pro tip. If you make a little graph with X on the X-axis and phi on the y-axis. Now, this graph I tucked into one of my pages in the last 2 days, so you can find it. But I'm telling you right now, if you're wise enough and thorough enough and smart, if you get this well enough, that you can tuck in a little graph where you put X on the X-axis, like meters, and phi, phase constant measured in radians on the y-axis, and you draw a straight line with a y-intercept of 0, that straight line represents how much extra phase we're getting for each unit of horizontal displacement, right? The slope of that line is what we mean by K. K is the ratio of phi to X. If you really think, and if you can explain that in your terms, right? Like the whole KX term in this equation is together, it makes phi. Phi is equal to K times X. Therefore, K is equal to phi divided by X. I'm saying a lot here. In theory, this is review, right? In theory, I'm just giving you pro tips now on how to handle this exam, given that I think we've covered the basic material. If you want to learn this thoroughly for the first time, it's still not too late, but go back to the earlier videos. But I'm saying if you can really show me that, okay, every time I say in English that this describes a collection of phase, every time I say in English that this is a collection of identical oscillators staggered in phase by a constant step, the step is K. What I mean by step is K is equal to the amount of phi, like the delta phi, the extra bit of phi that you get for every extra bit of X. If you made a graph of phi versus X, K is the rise per run in the phi X graph. It's the proportionality of how much extra phase delay or head start we get for every amount that we walk over on the x-axis of this arrangement. Again, if you're hearing that what I'm saying is important, but you're not like getting it, that's fine. You still have a couple of days to study and then like a week to do this thing. But make a note of what I'm saying now. Take the purpose of this to be, oh, this is important. I need to figure this out and talk to you. But if you are getting what I'm saying, if you're like, yeah. If you're like, yeah, I get it. Can you move on? Good. But please make a note to yourself that you get it. So you think it's obvious, whoever you are. If you think what I'm saying right now is obvious, that means it should be explained, not shouldn't. That's the mistake we all make. If you don't think because it's obvious, it's not worth explaining. It's the thing you want to show me that it's obvious to you. And those of you that what I'm saying right now is not obvious, don't despair. Just know I'm pointing you to what you want to figure out before Wednesday. Okay, let me go on. Sorry, I'm really, well, oh, something in the chat. No, I think that's just a hello. That's just a hello. Okay, yeah. All right, I'm going to change the view. So, but I'm going to break it down more. I'm not like leaving you. I'm not walking away. I'm just saying now as examples of what you would explain. Again, this is all in the context of question 4. Omega, I hope you realize at this point, omega is, and the units of omega, well, the units of omega are radians per second, right? Omega, I'm running out of, do I have room to write this? No, I shouldn't have erased it. Oh, sorry. Okay, so omega meant angular frequency. Please, again, remember, omega was something we understood and we've been working with whenever we were dealing with any individual oscillator, harmonic oscillator at all. And it's like the bulk of the rest of the test of your exam. Problems 1 through 3 are all about omega, really, right? Omega is the rate in time at which any one oscillator completes cycles. So it's number of cycles per second, but it's measured in radians. The whole key behind this whole thing is that there's 2 pi radians for every cycle. Like we learned that from the geometry of a circle, right? So omega is 2 pi over capital T, where capital T would be the amount of time in a cycle, right? So look down at the Y versus T graph on this page, the first graph, right? This is a Y versus T graph. It could just be the graph of an individual oscillator, right? It could be like where some individual oscillator is in vertical space for any given moment in time, right? That's what that first graph could just be. A movie, in effect, of a mass going up and down on a spring, right? Like you knew that first graph for like a month. That's what you're being tested on in the first 3 problems, but you've been studying that for like months, right? Now notice 2 things. One, between any 2 peaks on that graph, any 2 crests or any 2 troughs or any 2, like phase points, the amount of time between any 2 peaks, amount of time being the very thing that we're measuring on the independent axis, the amount of time for a full cycle from peak back to peak, from amplitude position back to amplitude position is what we call period, capital T. It's measured in seconds, right? So omega is in effect the reciprocal of that, but multiplied by a conversion factor of 2 pi, because there's 2 pi radians in every cycle. Okay, so that, but now also notice, like that graph could have been just one oscillator that we've been studying for months. But what it also is, if you think back to lab 3, what it also is if you actually did create wave ripples going back and forth across a long horizontal string in the lab, what that also is the graph of what you would get if you took a bunch of data, made a bunch of red dots on a movie. Well, let me back. So in lab 3, like you had ripples going back and forth, you had actual waves, and you made a movie of the whole thing, right? But then if you isolate a space slice of that movie, right? And this is what you did do in lab 3, right? You picked a particular, like you had this whole movie happening on your screen, and it was a movie of a wave or a bunch of waves in motion. But if you picked a particular X value, so in other, if you picked some value of X, some position on the X-axis, where, for example, perhaps, hopefully, if you were smart in your lab design, where hopefully you had stuck up a big like ruler or some kind of reference line in the back of your movie, or maybe it was just like a crease in the wall, some line in the wall, right? So if you picked some reference line in your movie, i.e. picking some horizontal spot that you held constant in your mind, and then you put a red dot wherever the metal of your slinky intersected with that line. You put a red dot there. And then the frame of the movie automatically advanced because that checkbox was unchecked under the movie settings, right? So you put a red dot in, and then the frame advanced by 1. So now the metal is up a little higher, right? On that, right? So you put a new red dot where the metal of the spring is. So and you do it again and again and again. So every time you put a red dot, in one case of lab 3, you're tracking the vertical progress in time of a particular horizontal spot of the wave, right? So this graph, right, and what you were seeing was vertical oscillation, cosinusoidal oscillation is occurring along a y-axis at any given X that you hold constant in your mind. Right? So you've extracted one relationship that is going on while waves are happening. You extracted the Y as a function of T relationship. And there it is, the first graph, the classic oscillation relation, right? And the period of time between any 2 successive peaks is capital T, the period. But then the thing that makes this all like a whole new thing is that on the other hand, you had this whole wave phenomenon. So you also stepped back and you did the opposite. You picked some moment in time and held it constant in your mind. We're not literally holding time constant, but you pick one moment in time and focus all your attention on that, i.e. you look at just one frame of the movie, and you put red dots at you put a red dot for where the height of the metal is at every next horizontal position, right? And you don't advance the frames this time. This time you have the checkbox under movie settings checked off where it says allow multiple points per frame, allow multiple points per frame. And you did that. You put in multiple points per one frame. And what did you see now? Now, this is new. This was as of lab 3. We didn't have this for any individual oscillation before. You see that if time is held constant, that y as a function of x is a cosine function, right? So what we're saying here is that a wave is ultimately a multivariable function. A wave is one, at the very minimum, one dimension of space being dependent on a different dimension of space and time, right? A wave is intrinsically two relationships happening at once. So this is why you had to make two graphs of it. You can't literally make one graph of this function at the top of the page. You can't, you would need a three-dimensional graph. You would need two axes and then a third axis, right? So you just took a time slice and a space slice of your wave and saw that they were both cosines. We're saying the reverse. We're saying, yeah, if you put time cosines together with space cosine, you get a wave, right? We're just doing the analogy. We're doing your lab 3, but analytically backwards, if that makes any sense. So in this bottom graph, the new thing saying that we're spreading out these oscillations in space now, and remember, each one of these graphs individually is not a wave. Each one of these cosines individually is not a wave, it's an oscillation. Put them together and you have a wave. So the bottom graph, the space between any two successive cycles, between any two given peaks, now it's called something different because now our independent axis is now space. It's x measured in meters, right? So the interval between two successive peaks on this graph is not an amount of time, it's amount of space or length. It's measured in meters. What do we call this thing? We call it, and this might be new. I mean, I know you know this from lab and you know this from like 7th grade, but I'm saying it now maybe for the first time in lecture. What you call that interval between two successive peaks of space, what the amount of space for one cycle of a wave is called the wavelength or the wavelength. It's measured in meters. It is the amount of space for one cycle. It's designated, oh, and I should make this very clear. It's designated with the lowercase Greek letter lambda. That is supposed to be a lambda. That's supposed to be a lambda. Maybe I'll make it a little bigger. It's supposed to look like that. That's a lambda, right? That means wavelength. And I'm saying lambda is to space as I'm saying wavelength is to space as period is to time. So and similarly then omega is to period as k is to wavelength. Right? Angular frequency is the number of cycles per second, and angular wave number is the amount of cycles per space. It's how. That's what it is. And you want, I mean, the more you can explain this kind of stuff in question 4, the more, and, say you go really to town in question 4. Say you go so to town, you're really proud of what you do in question 4, and you really think you've like really shined. And, another thing is, if you do question 4 right, one way you'll know you've done question 4 right is that when you're done, you'll be like, oh my God, I get it now. Like, this is another one of those things where the point is not, question 4 is not for you to prove to me what you already understand. The point is that if you do question 4, it will force you to see that you do understand. It will get you to understand if you do it thoroughly. You'll know and yeah, I can't emphasize this enough. The whole thing of a physics test is you learn it while it's not cheating to figure these things out while you're doing them. That's why you have a physics exam. And why I'm saying that is when you're done with this whole question 4 thing, you might step back and go, oh, that's the point. And then, by the way, if that happens to you, if you go, oh, that's the point, then if you're like most of us, then you'll have this next moment where you'll be like, oh, that's it? That's the whole thing? That's all? That's what he's saying? That's what he's making a big deal of? Like, and you'll either think, really? Is that, or you'll think, why didn't I get that before? Like the minute you get it, you'll think you were stupid for not getting it before, or you'll think I'm stupid for making a big deal of it. But no, don't listen to that voice. Just remember what it felt like 5 minutes ago when you didn't get it. Think about what it feels like now to get it and realize that is meaningful accomplishment. It's not that you were stupid before. It's that this is a heavy point. Anywho, once you've done question 4, one advice I would give you is if you go crazy on question 4, maybe you're even inspired enough to start your work with question 4. If you go crazy and really give me something that you think, oh, I really get this now, then when you staple your exam together, as long as you're completely clear on where everything is in your exam, you could put question 4 on top and have me read that first. If you think then I will be positively biased as I read the rest of your exam, that may well be. Put your best work on top. That's not a bad strategy, as long as it's clear. This is question 4. Like, don't, okay? But that's, feel free. Well, I'm going to go on now. Okay, so wait, I think I'm, but that's, I'm going to keep talking about this kind of for the rest of our course in a way, but that's, I think if you put together the last video with this, like really, and I'm not expecting you, I mean, obviously I've now spoken about it for 3 hours or something. A, that's because I'm not efficient, but B, because I'm trying to get you, you don't have to give me 3 hours worth on a piece of paper, you know, but I think I've now given you basically a full answer to 4 that ends essentially here. Okay, well, you can use your judgment. Now I'm going to go on and apply this even further. You can use your judgment as to whether you want to include this in your answer or not. But it may help you understand your answer better. But the summary is so. Wait, I'm sorry, I'm being unfair. Hold on, I'm about to go on, but just in case, let me pause for a second. Is there any question at all on essentially on question 4, either on something I've just said or something I said last week, or just in general on what I'm looking for question 4? Let me just pause for, or I'm going to write things for a second, but I'm not going to talk for a second. How nice. Wow, one person in the direct chat actually just like explicitly said, I have none so far. That is very helpful communication. I appreciate that. I will take that as, thank you. That is a good way of showing that you're with me, but you don't, fine. In fact, I'll even let that, so good. Thank you, one person, you know who you are, and please submit that for participation. And for the rest of you, I'm going to shut up for a second while I write something or some things. Please look through and ask yourself, I mean, we might have another opportunity Wednesday, but just see if you have a question. I am making a big deal of this. It means this is where, I mean, the other thing is that honestly, question 4 is like the place where it'd be the easiest in a way to separate people who are cheating from people who are not. I don't know how more to put it, but you know, question 4 is the place where you have the greatest opportunity to actually show your original and authentic and personal understanding. It is also the place where people who don't get what's going on and find something to copy from someone else will blatantly copy it. And we all know that. And I just got to remind you that I do know the difference. So question 4 is both the easiest and the hardest in a way, that way. So think, if you have any questions about it while I'm writing some things here. just to what this says here. Oh, okay, I just repeated what I just said a million times right here. It says, so this equation is a collection of phase staggered oscillators, yet it is also wave motion. Thus, wave motion can be made from a collection of phase staggered oscillators. But what is wave motion? This is a summary again of what, that's not an answer. What I just wrote here, if you copied this, and some people will, right? Obviously, some people are writing this down or getting these notes from me, but are not like totally listening right now. Some people will literally write that on their exam and hand it to me. That is not good. That's not what I'm looking for. This is a roadmap to you of what you have to cover in your exam to me. Like when you say collection of phase staggered oscillators, if you've been paying attention to me, you know that's an abbreviation. You have to say something longer than that. You have to say oscillators that are staggered in phase by a constant step. And you have to say like identical oscillators distributed along on it. Okay, I'm just reminding you again, that's an abbreviation of like a long thing you have to make clear. And then also when you say, so wave mode, but this is a summary that equation describes a collection, but it also describes wave motion. Therefore, wave motion is a collection. But why is that a revelation? What is wave motion again? It's motion from here to there where no individual particle does in fact move from here to there, right? You're going to explain that. So that's again, just a summary of what you're telling me. But now, given that, what time is it? So we have 25 minutes. Given that, watch this. Okay, so very quickly, what I'm asking now I'm moving forward here into a new realm, honestly. Remember what I was saying over and over a minute ago was like in lab 3, what you did is you took this overall phenomenon, this function of two independent variables, and you separated it into two relationships. The dependent variable as a function of one independent, like y as a function of t, holding x constant. And then you also did y as a function of x, holding t constant. What if we look at that mathematically? What if we take derivatives? What if we look at instantaneous rates of change, but one at a time like that? There's a procedure for doing that. Sorry. Okay, I'm going to say this a little bit quick. We've got 20 minutes. Okay. Here's the deal. From regular ordinary calculus, the infinitesimal rise in some, if you have a regular function of one variable x, the infinitesimal rise in that function equals the derivative times the infinitesimal run in that function. It sounds redundant. It sounds circular and stupid. It may be, but it's true, right? Like rise equals rise per run times run. It's just a way of saying if you want to know how high a function goes at some place, if you know its derivative and you multiply it by how far over it went, you'll know how high it went, right? It's just a way of rearranging, just writing the derivative in terms of its differential component. But now we're going to say, what if, for the first time now, we're going to say, what if we have a function of more than one variable, as physics is forcing us to look at here? What's the infinitesimal rise in a function of more than one variable? Well, it's hard to look at a function of more than one variable on one graph. We can't do it. We have to split into two graphs like we did over there. But what we'll find is that the infinitesimal rise of the function equals the rate at which it rises per space. If the function depends on space and time, then the rise in that function will be the rate at which it rises per space times space plus the amount at which it rises per time times time. But in other words, I'm saying mathematics allow us to do exactly what you did in lab 3 for a multivariable function. In math, if you have a function of more than one variable, you can look at individual rates of change one at a time, independently. If the function depends on more than one independent variable, then the independent variables are truly independent of one another. So you can look at the way the function rises per each of those independent variables by itself, as long as you temporarily, mentally, hypothetically hold the other one constant, just like you did in lab 3. Like you can look at the slope of your YT graph, paying not at all attention to any X graph because you picked one value of X for doing it, right? When we do that, that's called taking a partial derivative. And it's signified with this weird symbol here, this backward 6 thing. It's called partial.
I don't know, it's a Celtic symbol or something, but so partial y, partial x is called the partial derivative of y with respect to x. And it means literally taking the derivative. If you write out the function, it means taking the derivative of y, treating x as the variable, but holding t, treating it as a constant, as you did in lab 3. Partial y, partial t would be the same in reverse. And what we're saying is you put those together and you get the full rate of change of the whole function. So I'm going to do a quick example, not a hypothetical example. I'm going to show you with our wave equation what we would do. Let's take partial derivatives of y equals a cosine omega t, let's say plus k x. Now, like omega and x and k are the constants, but this is a function of two variables, x and t, right? So first I'm going to take I'm going to take partial y over partial t. I'm going to do this a little bit quickly, but not that quickly. I'm going to take the derivative of y with respect to t. That means I'm going to treat x as a constant. I'm going to pretend that it's just a letter that's not changing. Okay, so the whole thing, kx, is a constant. So I will get negative a omega sine of omega t plus kx. In other words, this goes back to that exercise from homework 2 where we had the 3.5 sitting there. If x is a constant, if I'm treating it as a constant, this is like looking at your YT graph in lab 3. I'm not saying x really doesn't change. I'm saying in my mind, I'm picking a particular value of x and seeing how y changes relative to t as long as x is held still. So k does not come out from the chain rule because and neither does x because they're a constant. The derivative of a constant is 0. So I get this. If I do it again, I would get this. That's taking two time derivatives of our wave solution. Now I could do the other thing. I could go to, and I am going a little faster now. Hopefully you're still with me, but now I'm going to take partial derivatives with respect to space. Same equation, like y equals a cosine omega t plus k x. But now I'm taking the partial derivative of y with respect to x, right? So now so I should make it like over here, what I did was I treated x as a constant. Now I'm going to treat, now I'm going to treat time, t, like it's a constant. So so, the derivative of a constant is 0, right? So now on this one, the derivative of omega t is 0. So nothing comes out from the chain rule from that, but the k of the x comes out. So I get negative a k sine of omega t plus k x, right? And then I do it again. Why am I doing it again? Because I always do it again, because second derivatives. So I do it again. And why is physics always about second derivatives? Because F equals MA. It doesn't equal MV. So I do it again, and I get a K squared cosine omega t plus K over X, right? So now I've taken, so you see, now there's two different ways to take two derivatives of this equation because there's two different variables, and I'm looking at rates of change of one at a time while holding the other fixed. It's like the experimental method that you did in lab 3. So now what's the point of all this? Well, now notice, we were from previous page. We had this. right? But now look at those. So we have two different equations now. The second partial derivative with respect to time and the second partial derivative with respect to space. They're different ideas, but they look very similar. They both contain that cosine omega t plus kx term, and they both contain negative a. So they seem to be related to each other. So in fact, let me rewrite each one. Let me rewrite each one just in terms of, let me isolate that cosine term from each one since it's the same. So I'm going to rewrite each result in terms of that common cosine expression, or that common, which is the phase of the wave, so to speak, right? So I'm going to say, like the time equation is cosine omega t plus kx equals d all over negative a omega squared, right? The time equation, this is messy. Okay, that's the time equation. And then the space equation right? Very similar. It's just that one has the time goes with omega and space goes with k. My k's are completely illegible. Okay. But those are each an expression for the cosine thing. So set equal to each other. So I can say, and I can go back if you want, I'm just trying to, so I can say over negative equals right? I mean, I'm just setting the two equations equal to each other. So the second time derivative, the second partial time derivative over negative a omega squared is equal to the second space partial derivative over negative a k omega squared. Well, the negative a's are on both sides. We can divide both sides by negative a, so they all cancel out. The negative a's cancel out. So then I can multiply both sides by the omega squared and be done, I can say. Oop. Okay, we have 5 minutes left. We did it. That's pretty cool. Okay. We're going to spend all of next Wednesday. I mean, we're going to spend all of this Wednesday backing up and really looking at what this means. I think you saw it at the end of lab 3 and probably had no idea what you were saying, or maybe you did, but this is a second order partial differential equation known as the wave equation. This is a differential equation. It's the second one we've gotten this semester. It's very, very similar, but yet different from the first differential equation we got this semester. This is the differential equation that describes wave motion. Anything that satisfies this equation is a wave, or is wave motion, and any wave motion in the world must satisfy this equation. This equation is a second order differential equation like our old one, but this one's partial because it deals with a function of more than one variable. This one is very much like our Hooke's law equation for harmonic oscillation, right? If you look at the left side of this equation, it's partial symbols, but it's very similar to the it's identical to the left side of the Hooke's law equation for simple harmonic oscillation. The left side here says the vertical acceleration, the rate of change of the vertical position of any particle. Well, the left side is referring to the instantaneous rate of change and the rate of change of the vertical position of any particle. It's talking about the downward or upward acceleration of a particle. And it's just like the original equation. It's saying that the acceleration of a particle is directly proportional to something, is equal to a constant times something. In the original Hooke's law thing, which is the first 3 problems of your exam, the whole idea is that the rate at which a mass on a spring accelerates back to the equilibrium position is directly proportional to how far it is from the equilibrium position. That's what oscillation means. You race back home at a rate that is determined by how far away from home you are. That is elasticity. This says something incredibly similar, but it hikes it up one more dimension in space. This says if you pick any particle in a wave pulse, if you pick any particle, the rate at which it accelerates home to the x-axis, the rate at which a particle in a wave accelerates back to the equilibrium line is directly proportional to how concave the medium is at that point. For a mass on a spring, the farther away you are from the equilibrium point, the faster you race back to that point. For a wave, the more bent away from the equilibrium line you are, the more concave, right? Second derivative of y with respect to x in math class is called concavity, right? The more concave, the more distorted, the more disturbed the metal spring or whatever, the medium, the more disturbed or concave or distorted from flatness a bit of the wave is, the faster it races towards flatness. This is restoration, oscillation, but toward another axis of space rather than to a point of space. This is oscillation in time and in space. The second partial derivative with respect to time of any particle anywhere in a wave is directly proportional to the second partial derivative with respect to space for any point in every point of time and space in a wave. For the last thing I'm going to say, I see the time. For Hooke's law for oscillation, acceleration was directly proportional to displacement. Here, for a wave, acceleration is directly proportional to concavity, to distortion, to disturbance. The constant of proportionality is omega squared over k squared. Omega is 2 pi over time. K is 2 pi over space. 2 pi over time over 2 pi over space is space over time. Look at the top of the page. Omega over k is just a fancy way of saying lambda over t, wavelength over period. Omega over k is a fancy way of saying space per time. The constant of proportionality for the wave equation
is the speed of the wave. It's a glorious equation. It packs a ton of information into one linear statement. We will unpack and refresh. I know that went fast. We will unpack and review and refresh all of that this Wednesday, but that's the bottom line. That's the wave equation. It came from taking two partial derivatives of your cosine expression of phase staggered oscillators. Okay, I'm done. Have a very nice day. I'll stay for a second if you have any questions. Okay, have a great day. Great.
Have a great day, Professor.
Thank you, Ice Cube. Back to Amy. Thank
Have
you.
a good day.
Have a great day. Thank you. Have a great day. Bye. Bye. Bye.